Let us understand the concept of relative velocity using a swimmer in a flowing river. The river flows horizontally with a constant velocity. The swimmer swims with a certain velocity relative to the water. From the ground frame, the swimmer experiences both motions simultaneously. The velocity of the swimmer relative to the ground is the vector sum of the swimmer's velocity relative to water and the river's velocity relative to the ground. When the swimmer swims perpendicular to the river flow, the river carries the swimmer downstream, resulting in a diagonal path. This diagonal arrow represents the net velocity of the swimmer. If the swimmer swims downstream, the velocities add up and motion becomes faster. If the swimmer swims upstream, the swimmer can move against the flow only if the swimmer's speed is greater than the river's speed. Now let us change the frame of reference. Instead of observing the swimmer from the ground, we observe the swimmer from a boat. That is drifting with the river, and therefore has zero velocity relative to the water. In this frame, the water appears to be at rest. To move into this frame, we subtract the river's velocity from all velocities measured from the ground. The velocity of the swimmer relative to the river is equal to the swimmer's velocity relative to ground minus the river's velocity relative to ground. This vector difference gives the relative velocity of the swimmer. Graphically, this is obtained by reversing the river's velocity vector and adding it to the swimmer's velocity vector. The resulting arrow represents how the swimmer appears to move when seen from the river. Thus, relative velocity is not a new motion. It is the same motion viewed from a different reference frame. Understanding this vector difference removes confusion between net velocity and relative velocity.